Okay, so let us start our discussion on quantum statistics. So as you can see in this title slide, that in this lecture we are going to have an introduction for the quantum statistics. Then briefly we'll talk about the consequences of this indistinguishability of the particles. So that's going to be one of the major change that you will see from the classical statistics to quantum statistics. Then we will start talk about the first part of the quantum statistics, that is Bose-Einstein distribution or Bose-Einstein statistics. Okay. So as we have seen in our classical statistics, that Maxwell-Boltzmann statistics, which was briefly majorly covers under the classical statistics, could explain the distribution of energy and velocity of the particles if to a fair bit of accuracy. Okay, but when it comes to electrons in a metal, which you can consider to be electron gas, like free electrons, so which we can consider to be as the electron gas in the metal. So when this Maxwell-Boltzmann statistics was applied to explain their phenomena, and it could not explain the observed behavior of the electrons in a metal. Similarly, as we have seen while trying to explain the photons or the electromagnetic radiations that are present in an enclosure at a particular temperature that we have seen, right? So there the classical ideas did not work. In fact, when the Maxwell-Boltzmann statistics was applied to this photon gas, so here is a collection of photons, right, within the enclosure, so these are called photon gas. So when it was the classical statistics or the Maxwell-Boltzmann statistics was applied to that, then it could not explain, which you have seen, right? So there was a change of ideas regarding how do we explain the observed behavior of this, the behavior of electrons or behavior of photons. So then we have seen in the previous few videos that the concept of the photon has come into play, right, where the exchange of energy between the matter and the radiation happens in some discrete quanta of energy, which we call it photons, right? So going by that line, right, so now we have to develop a new statistics, which we are calling it quantum statistics, right? So let's try to understand one by one. Okay, so majorly in this video or in this lecture we will talk about the Bose-Einstein distribution. Okay, later we'll talk about the Fermi-Dirac distribution, which is the second part of the quantum statistics. Okay, so Bose-Einstein statistics, right? So it was developed by S.N. Bose. Okay, we can be proud of that. He's an Indian scientist, as you all know. Okay, and later on it was generalized by Albert Einstein to describe the energy distribution for the particles whose spin angular momentum were integral multiple of h cross. So okay, so here this in the classical particles you did not see anything, or you did not have any mention about the spin angular momentum of the particle. Okay, now when you come to this quantum statistics or the quantum physics, that there is some intrinsic parameter comes into play. Okay, this is spin angular momentum, or colloquially or typically we call it spin of the particle. Okay, so and these photons, right, the quantum particles or the particles whose spin angular momentum are integral multiples of h cross. Okay, h cross is a h Planck constant by 2 pi. Okay, so these particles are known as bosons. Okay, similarly for the fermions you will see meaning. Okay, so and then the wave function corresponding to the bosons are symmetric. What do I mean by this? Suppose if I have two bosons, okay, and I have a wave function is I can write, so this r1 r2 position vectors of these bosons. Okay, so if I interchange these two particles or two bosons, what will happen? So there, meaning if I interchange, the wave function will be simply, so interchange of these positions, so it will be, so r psi 1 comma psi 2 will be equal to psi r2 comma r1. Okay, so meaning the wave function is symmetric. Okay, so and here, as you all know, the Polish exclusion principle, where in a quantum state only one particle is allowed to stay there, right? Only, okay. So in quantum mechanics, according to Pauli's exclusion principle, so one quantum state can be occupied with only one particle. Okay, so that principle is not applicable to bosons. Meaning what? In a quantum states, more than one boson can occupy or can sit in that quantum state. Okay. Now the examples of bosons are alpha particle with spin 0, photons with spin 1, deuteron we have spin 1, similarly pi mesons with spin 0. Okay, so these are few examples of bosons. Okay, you can find many other bosons like this. Only thing you have to remember is that these bosons are those quantum particles or particles which having the spin angular momentum are in the integral multiple of h cross or reduced Planck constant. Okay. Now, the another set of particles which we will cover in Fermi-Dirac statistics. Okay, it was developed by Enrico Fermi for the electrons mainly. Okay, and its relation to quantum mechanics was established by Paul Dirac. Okay, and here the nature of these particles are that this energy Fermi-Dirac statistics describes the energy distribution of the particles whose spin angular momentums are, okay, so n plus half h cross. Okay, what you need to do is that if you have odd multiples of, okay, so you can take this, so if you have odd multiples of this h cross by 2, meaning if I write n equal to 1, so you will get h cross by 2. If n equal to sorry, in the first case n equal to 0, you will get h cross by 2. If it is n equal to 1, you will get 3, okay, multiplied by h cross by, similarly 5 h cross by 2. So whenever you have odd multiples of h cross by 2, what? This spin angular momentum. If it is odd multiples of h cross by 2, those particles are fermions. Okay, so in other case, if you compare in the same manner to the bosons, those are integral multiples of h cross or even multiples of h cross by 2 if you want to compare, like, you know, term to term. Okay, and here this psi, the wave function corresponding to fermions, is antisymmetric. What do you mean? So if I have a wave function like this, how we have written for bosons, it will be equal to negative of, if I exchange the fermions, so it will be psi 2, let me just clean it up here. Okay, so it will be psi, so it will be minus of psi r2 comma r1, so there will be negative sign. Okay, so regarding this antisymmetric and symmetric, we will learn little later in much more in detail, as well as if you want to learn straight away, you can see some topics in quantum mechanics. Okay, I think you will get more information in that. And here this Pauli's exclusion principle is applicable. So since these are electrons, we all know that, right? So the electrons follow this Pauli's exclusion principle, where in one quantum state only one electron can occupy. Okay, similarly examples for the fermions, these are electrons, positrons, where you will see the spin angular momentum is half. Similarly for protons, neutrons, mu, mesons, and so on and so forth. You can find another examples of fermions as well. Okay, so having a fair bit of introduction to quantum statistics, which are basically two types that we are going to study here. This is Bose-Einstein statistics and Fermi-Dirac statistics. Okay, so in this lecture we will start with Bose-Einstein statistics. So later videos or later lectures we will talk about this Fermi-Dirac statistics. All right, so let's talk about, yes, before we start, as I said in the beginning of the lecture, that indistinguishability of these quantum particles. Okay, so in classical particles, we have seen that if you have two particles, we can identify them with, let's say, A and B. They are two different particles, and I can identify them with, let's say, particle A and particle B. Okay, or let's say color of one is black, one is white, or something like, I can have some identification mark to identify these two particles. Okay, so if I have these two particles, two distinguishable particles to be distributed in two compartments, let's say, so this we have done it in past. Okay, so let's say I have a box like this to be distributed. Okay, so how many ways I can distribute them? So I can have A, B, one distribution, right? I can have Another distribution I can have BA, okay, and these classical particles do not follow any this Polish exclusion principle. So meaning what, in one compartment or one box there can be more than one particles. So then I will have, let me just complete how many of I can draw, right? So I can have AB in this, and then probably this first one will be empty here, then AB here, okay? So I can have 4 different arrangements. So these are different ways I can arrange these 2 distinguishable classical particles, okay? Now come to Bose-Einstein statistics, what happens? So these are applicable for bosons, and bosons are indistinguishable particles. So regarding this indistinguishable particle, we have talked very briefly in one of the earlier videos, okay? So in this case, what will happen? Let me try to draw again, okay? So here, so I will not be able to identify as A and B, either both will be A, both will be B, right? So okay, so here what will happen is particle, let's say, so one particle can be here, another particle can be here. It's one way of distributing that, okay? Then second case, it could be, okay, I'll have one more case, so let me just complete this, okay? So okay, so I can have both the, so in Bose-Einstein statistics, these are bosons, right? So bosons follow Bose-Einstein statistics, so 2 particles can be in one state, no problem regarding that. So I can have both the particles here. So why am I drawing as a, not writing A and B? Just to show you that both are identical, okay? So and in third case will be like this, okay? So more than one particle can sit inside one box if it is a boson, okay? So as you can see the difference, right? So now in Fermi-Dirac statistics, you will see that you will have only, sorry, let me use the similar color, okay? Okay, let me draw, yeah, sorry, okay. So here, since one particle can sit only in one state, so see, I have no other option but to have this, okay? So how many ways I can arrange these 2 particles, 2 fermions in 2 states? There is only one way. Even if I interchange, they are indistinguishable. So it's not going to give you a new state or a new configuration or new ways of arranging them, okay? So you have to keep in mind. So what is the difference in classical statistics? So you could identify the particle, each one of them. Now think about these bosons, right? These are photons, let's say. You cannot identify them, oh, this is one photon, that is another photon, okay? Similarly in electrons, there is, all electrons are alike in this case, okay? So now let's try to start discussing on Bose-Einstein distribution law. Okay, so now we need to learn about few postulates. As we have seen, any new theories come up, we always go with some kind of assumption postulates to start with, okay? So here, the particles of the systems are identical, which already we have talked about, and indistinguishable, okay? And any number of particles can occupy in a single cell in a phase space. This also we have talked about. Yes, the size of the cell cannot be less than HQ, where H is a Planck constant. Now this is something which we have learned in while trying to understand the size of this cell, the phase cell, right? While trying to discuss about the phase space, okay? So H, so we are in the quantum regime, so the H cannot be as small as that you want. So it has got a limitation on that. So H has to be, the size of the cell has to be H cube, and H is here Planck constant, okay? And regarding this, number of phase cells is comparable with the number of particles. This also you have to keep in mind, okay? Okay, so this N by G, so the occupation index which we have discussed in the previous video, which is, you can say that it's nearly equal to 1, okay? So this is approximately equal to 1 or nearly equal to 1. N by G is your occupation. So I had talked about regarding this f of this distribution function that you will talk about in this lecture as well. Occupation index, same function will mean different thing. It's also, I have said that it's a probability of occupancy of this state, okay? So here it will be nearly 1 as it is stated, okay? And of course this Bose-Einstein statistics is applicable to bosons or the particles which obey this Bose-Einstein statistics. These are called as bosons. All right, now let's try to develop the distribution law where we have done it for classical particles. Okay, now let us consider a system consisting of n independent indistinguishable particle. Okay, so n of them we will consider, and let's say these particles will have definite energy, right, meaning it have got its own momentum, and of course it will occupy a definite position in the space. So it has got positions as well as momentum. Okay, so yes, so therefore they can be represented by phase point in the phase space. Okay, so in order to determine the energy distribution of this particle in the most probable state, so we will try to talk about the distribution in the equilibrium state. We divide the available volume in the phase space into large number of compartments where each compartment represents small interval of energy. Okay, so here is our job to do. So let's say this is my volume. Okay, so this is my entire phase space. Okay, so entire available volume for these bosons. Okay, so I will make now few compartments. Let's say compartment 1, let's say compartment 2, let's say compartment 3, compartment, okay, it can be anything. Okay, I'll simply draw as many as you want. So what you will do now, this is, let's say, compartment 1. Okay, this is compartment 2, 3, 4, let's say this is ith compartment. Okay, and eventually I have, let's say, k number of compartments, and this is, let's say, I plus 1 or something like that. So there are so many of them. Okay, so each compartment here, as you can see, these are unequal size, so I have to use concept of cell here to see the distribution of these bosons in this. Okay, and so what I will do now, I will make cells of so each compartment will be further divided into smaller cells of equal size, right? So I will not draw, I will just representatively I will draw for one. Okay, so this each cell that you see in different compartments, let's say in this compartment. Okay, so the size of the cell, as we have done in the earlier lecture, so this size of the cell in across various compartments you will see equal. Okay, and typically this size of the cell is, as you have seen, this is the HQ, which is much smaller number, and that's why the number of cells per in the compartment will be way larger. It's a very large number. Okay, so what you will do now, so this number of cells in a compartment will be represented by the letter G. Okay, so I have G1 number of cells in the compartment 1. So this each compartment represents one energy level. So in the energy level 1 there are G1 number of quantum states. That's what you have to remember. Okay, so in let's say compartment number 4 there are G4 number of quantum states. Okay, corresponding to the energy level 4, E4, let's say. Okay, so there are okay, so similarly GI number of cells are present in the ith compartment, or each compartment represents a energy level. Okay, and a GI is what? These are number of quantum states available at that ith energy level. Okay, now the distribution that we have to do, okay, which we have done. So let's say there are total number of n particles, as we have seen. So out of that, n1 particles, or this n1 bosons now. Okay, so n1 bosons will be, let's say, so now we are trying to define the macro state. How? Out of the total n particles, n1 bosons are there in compartment 1. So n2 number of bosons are there in the compartment 2. Similarly, you can keep going, and ni number of bosons are there in ith compartment, and in nk number of bosons are there in kth compartment. So we need to now see that how many ways I can distribute these bosons in this entire, meaning energy states or energy levels, so different energy levels. So, and this compartment 1, as I said, represents the energy level 1 having energy E1. Okay, so the corresponding energy for this first, let's say, E1, similarly this is E4, and this is E3, and EI, EK, all those things. So idea is what? You have n number of bosons. Out of that, we have to distribute n1 into compartment 1 or the energy level 1 having energy E1, n2 to compartment number 2 having energy E2. Similarly, ni number of bosons in ith compartment having energy EI, and corresponding to each of these energy levels or the compartments, I have Gi, if for the ith level, I have Gi number of cells within there, which correspond to that many quantum states available for that energy level. Okay, so idea is to now calculate the number of microstate for that macro state. Yes. Okay, so this n1, n2, n3, and as I have said here already, I think I have explained fair bit. Okay, so having mean energy, yes, so I have considered these energy levels or the energy for corresponding each of this compartment, right, numbered as 1, 2, 3 for all the way k, containing this Gi, meaning G1, G2, G3, Gi, Gk cells corresponding respectively in them. Okay, so then total number of particles, we know that these are constants which will be equal to sum of the particles in each of the compartments or each of the energy levels. So that will be n will be equal to sum of the number of particles in each compartment or each energy level. So n1 plus n2 all the way ni, then plus nk. Okay, now I need to find out a way how can I calculate number of ways to distribute these so many particles in the entire space, okay, entire volume. Okay, now let's just consider ith compartment, then I will generalize for each one of them. Okay, now let's consider ith compartment. So I have how many ni number of bosons are there in the energy state? Ei, I mean the mean energy of that energy level is Ei. Okay, and ni is the number of bosons for that. Okay, and how many cells are there? Gi. Okay, now suppose I assume that these ni particles are arranged in some linear way, okay, in a linear array, let's say. So what I mean by saying that, I have, let's say, sorry, so I have, let's say, okay, like this, okay, and let me just put it, okay, these many boxes are there. How many of them will be there? That G1 of them. Okay, so I'll just put a bit of dash just to make sure that you know there. So there are total how many are there? There are like total you can have Gi number of cells are there. So I have put dash. Okay, so I need to actually show you only few, then you will understand what I am going to do in here. Okay, so all right. So I have ni number of particles, Gi number of boxes, meaning cells here. Okay, just consider boxes here I will talk about. Okay, so ni number of particles and Gi boxes. So I have arranged them in a linear fashion. So if I have G1 box, Gi number of boxes, how many partitions are available for me? One will be less, right? How many boxes? Because if I have okay, so the n points are fixed. Okay, this n partition, this end partitions are fixed. Okay, inside that how many we'll have? We'll have just wait. Okay, so I will have so Gi minus one partition, number of partitions in the box. So I am counting these partitions. How many of them? So because I have Gi boxes, so I will be having one less number of partitions. Okay. All right. So okay, and then I have total number of Ni particles. So I have to arrange these Ni particles in Gi boxes. But way I will sort out the mathematics is that, so what I will do, so total particles here to have that permutation combination, I have this Ni particles and let's say plus, so Ni particles plus this many particles to be arranged among themselves, because here, these are bosons. So in a compartment there can be more than one particle. It could be 3, 4, 5. Meaning it can all Ni can go to one box as well, right? That is one of the ways to arrange. Okay. So total number of ways to arrange this Ni particles in Gi boxes, way is that. So what I have to do, so I have objects to handle with this Ni plus how many partitions? These are also, you can think about another objects. Okay, Gi minus 1. So this much factorial number of ways I can arrange in this linear fashion. Okay, I mean, you need to understand this. So what I have done, I have ni number of particles to be distributed in gi number of boxes. What I have done, I have ni number of particles. Then I have counted the number of partitions in the boxes. So n two things are fixed. Okay, within this, how many partitions I will have within the big box? I will have gi minus 1 number of partitions. So I have ni number of particles plus this many objects, gi minus 1 numbers, to be playing around to form the partition, or to arrange them, okay, in different ways. So total particle to be, to form that arrangement is ni plus gi minus 1. That many factorial number of ways I can arrange this particle. I can have that many arrangements, okay, to have different ways to arrange these particles. However, here we know that these bosons are indistinguishable particles. So if I just interchange two of them, because which is covered here in this factorial term, I am not getting a new ways. Okay, so I'm just counting few arrangements twice, or maybe thrice, or maybe many times. Okay, so what I have to do, I have to divide by ni factorial times. Similarly, the partitions are also identical to each other. If you just switch the two partitions, it's not going to give you a new distinguishable arrangement. It will look alike. So that means gi minus 1 factorial also I have to deduct. I mean, like, we have to divide the entire number of the ways that you get. Okay, so that you have to divide by gi minus minus 1 factorial. So this many ways. So this is the actual number which you will get. So this many ways you can arrange these ni bosons in a gi number of boxes. Okay, so this is for the ith compartment. Same thing I can repeat for each and every compartment, right? So then I will get, so the number of ways to distribute ni particles in gi cells. So okay, so I have used the term boxes. Now you just convert it to cells of ith compartment is given by this, which is what I have written here. Okay, so now similar expression I can obtain for each one of them, and things are independent. Each compartment is independent of each other, right? So how many ways? So for compartment 1, compartment 2, so I will get similar expression for all each of the compartment. What I have to do, simply multiply each one of them. So I will get the total number of ways to arrange the n1 bosons going to compartment 1 having energy E1, n2 number of bosons going to energy level E2, okay, meaning similar to ni going to ith compartment, nk number of bosons going to k compartment. I will get that. So number of microstate for that macrostate is given by this expression. Okay, now our idea is to find out the most probable state, or the equilibrium state. Okay, so what you have to do, again, take logarithm, because these are very large numbers. Take logarithm, then you differentiate, equate it to 0, and then carry out our usual maths that we have been doing for our previous distributions that we have found out. Okay, so now here this ni and gi are really very large numbers, so I can drop this minus 1 from this, right? Okay, so if I drop that, okay, so I will remain with this, and then now from now onwards, like usual maths that we keep doing. Okay, so I take logarithm both side, natural log, so ln w equal to, so product, so it will become, you all know, I think by now it's very familiar, ln a dot b will be ln a plus ln b, which you all know that. Okay, so sum over going from I going from 1 to k, then from the numerator you will get ln this, and from denominator ln I factorial ln g I factorial. Okay, then again you have to apply Stirling approximation, because you all know ln n factorial is n ln n minus n. Okay, because this n is very large number, right? So you can apply Stirling approximation. So while doing so you need to apply Stirling approximation for each of this term, right? Okay, so I think, yeah, this is here. Okay, so after applying, doing our normal maths, and then I will get few things cancelled out. Yes, so this term will be cancelled out by this ni and gi. Okay, so I hope you can see this. Okay, so if you do it for yourself, you will know. So this is negative of ni plus gi, so this is ni, this is gi, so this will get cancelled out. So I will remain with this expression. Now what you have to do to maximize, Okay, for the thermodynamic probability, we need to find out d ln W equal to 0. As it is, here the variable is Ni. Gi is constant. Gi is not going to change. There is a number of cells present in each of this compartment, or number of quantum states in each of the energy levels. Ni is a number of particles which are present. Okay, in equilibrium, what will happen? As I said, some particle, because of this collision, you will gain energy and then go to higher energy level, or it will come down. Some of them will lose energy. So that's why Ni will keep on changing. So that's our variable. So doing usual maths, there is a ln W. So if I differentiate, so I will remain with, so I'll keep this, so I have to differentiate it. So Gi is constant, so this is as it is, ln Gni plus Gi multiplied by Dni, and differentiating this term with Dn, meaning that with Ni, then I will get this. Similarly, these two you will get as it is. Okay, then a few things. So this will get, I will remain with 1. Similarly, this I will get 1, and I will have -1, then this is +1. So this will also go off, so I will remain with this. Okay, so here maybe one thing we need to check out. This should have been, I think, negative. Okay, this part is negative. Okay, so because this is negative sign, please make a correction here. This is negative sign. Okay, so now so I have to equate this to 0, right? Yes, so because of negative, it will come in the denominator. Okay, so this is, it will come in the denominator, then I will just simply switch the numerator and denominator. One minus sign will come, and then I have to equate it to 0 because of this. We are trying to find out the maximum thermodynamic value. There's a condition for that, right? Condition for most probable state. Okay, so I will, but I get this minus sign, since right hand side is 0 multiplied by -1 on both sides, I will remain with this expression. Okay, now in addition to these conditions, we all know that number of particles in the system is constant, so the system must satisfy this conservation of total number of particles, which is given by this. Sum of the particles in each of the compartment, each of the energy level should be equal to a constant, and it is n. And so if I differentiate that value with meaning it's a constant, so if I take differentiation, it will be 0. So that means sum of change over Ni, meaning the, which the individual Ni may not be, so change in individual Ni may not be 0, but if I club them together, sum them together, it will be 0. So overall the total number of particles is not going to change. Okay, so this is this condition we have seen in past as well. Similarly, the conservation of total energy of the system. So the total energy of the system is constant. Okay, so dE will be equal to 0, but then this sum over, this is I. Okay, sum over I, EI dNi will be equal to 0. So now we have to, what we have to use? Lagrangian, yes, method of undetermined multipliers, right? So what do you have to do? Multiply this by this equation by alpha, and one of them by beta, and then sum all of them, right? So this you have to multiply by so this you have to multiply by alpha, this you have to multiply by beta, and then you take like sum with this third equation you can write. So all 1, 2, 3, sum them up. Okay, so you will get this expression. So now on, just keep on following. So now this I have talked about a whole lot of time, that since this is right hand side is equal to 0, so this is the linear combination of like linearly independent expression. So each one of them term has to be, so you can think about like a coefficient, this term, which has to be equal to 0, because the change of the Ni is independent of each other. Each of them has a change in, let's say, in the compartment 1 is independent of what is happening in the ith term or kth level or kth compartment. Okay, so that's why each of the coefficient has to be equal to 0. So I will get this, then I switch over, shuffle this alpha beta term to the right hand side, and this is what we get. This, if I take exponential both sides, and then switching this numerator and denominator, I will get this, and then I take this 1 to the right side, I will get this. This is Gi by Ni equal to exponential alpha plus beta E minus 1. So beta, you should not forget, this is 1 by kt. Okay, so now, so I get this, so I shuffle this Ni Gi, so the this this is the expression that we need to mark it. So Ni equal to Gi by e to the power alpha plus beta e minus 1. So this is the distribution function. Okay, so then substituting for beta, you will get this expression where you have this beta is equal to 1 by kt has been substituted. Okay, so this equation represents the most probable distribution of the particles here, bosons, in among the various energy levels for system obeying Bose-Einstein statistics. Okay, and this is what known as the Bose-Einstein's distribution law for assembly of bosons, or you can just simply say this is expression for, so the Ni equal to this term in the right hand side is a Bose-Einstein distribution law or distribution for the assembly of bosons. Okay, so similar thing we have got for the Maxwell-Boltzmann statistics as well. Okay, but the expression is not same. You need to pinpoint the difference, right? So this is for discrete energy level. So we can have for the continuous values of energy as well, right? Okay, but before that, let's talk about the energy distribution function. So this is distribution law for the particles. Okay, and so energy distribution function f of EI is the average. So this we have talked about in the previous video, is the average number of particles per quantum state in energy level EI. So in the ith compartment or ith energy level, you had mean energy is EI, whereas it has got many like GI number of quantum states. So what is the average occupancy or average number of particles that are present in that quantum states? Okay, so in the energy level EI is given by simply Ni is the number of particles which are present in the energy level I, right? So by GI, so this is simply given by this we have derived here, right? So I've just shuffled this G2 down. Okay, so and for continuous distribution of energy, same function can be written like this. So this is a energy distribution function, the Bose-Einstein energy distribution function, right? So now how I have written for the particle. So for the particle distribution function for continuous values of energy, I can write. So if NEDE is the number of particles whose energy lies between this capital E and capital E plus DE, within that range DE. Okay, so how can I write? Simply I have to substitute for all these numbers, right? So here, so this expression, same expression, just I have to introduce the continuous variable, the E. Okay, so the NEDE is equal to G. So the here this part is interesting, right? G of EDE divided by the factor that which we have got, e to the power alpha, then e to the power E by kt minus 1. GE is what? This we have derived, you have talked about in the last video as well as in the previous lecture number 11, 12 as well. Okay, so this represents the number of states which are available in the energy range E plus so E and E plus DE, right? E and E plus DE. So the number of states available in this. Okay, and which also called as density of states. This you have to, okay, this is density of states. Okay, substituting for that expression, you will get this. Okay, so this is Bose-Einstein energy distribution law for continuous distribution of energy. Okay, so this represents what? So this is the number of bosons which are present or the distributed in the energy range E and E plus DE is given by this expression, where V is the volume, mass is the mass of these bosons, H is the Planck constant, remaining, and E is the energy, and then all these factors. Okay, so I hope I have given a starting sort of a flavor of what quantum statistics is look like. Okay, so we will talk more on the Bose-Einstein or bosons, its behavior, how does it behave at what are its partition functions and other topics related to the Bose-Einstein statistics or bosons. We will talk about that. Okay, so we will specifically talk about the photon gas, which are actually bosons, which we have started our discussion with from the so the photon was the main thing because of which we had started talking about the quantum statistics or like Bose-Einstein statistics in this. Okay, so for time being we will stop at this point. Okay.